Hello, I'm David Hyam, and today I'm going to talk to you about the paper A No Reference Model for Detecting Audio Artifacts Using Pre-Trained Neural Networks. This work was completed in collaboration with my colleagues Ayush Bagla and Vineta Haralampieva. The three of us are members of the video quality analysis team within Prime Video. In this presentation, I will first describe what audio artifacts are. I will then move on to describing the model itself. I will talk a little bit about the dataset that we use to develop and validate the model. I will then present some results and finish up by describing the future work we intend to complete. So what are audio artifacts? Audio artifacts refers to the sonic material that is accidental or unwanted. This may be introduced at production time, for example the hum of an electrical appliance, or it may be introduced during the editing process. However, ultimately it has a negative impact on a viewer's quality of experience, and subsequently we wish to identify and mitigate it. This work creates a model to detect 4 different audio artifacts. I'll use the figure on the left of the screen to illustrate each of these defects. The top row of the figure illustrates a clean, non-defective audio sample. On the left-hand side we have the waveform, and on the right-hand side the log-mel spectrogram, which is used as the input to our model. Each of the subsequent rows illustrates one defect, with the defective period in the non-grayed area. The impact of the defect is visualized clearly in the log-mel spectrogram. The first defect we consider is audio hum. This is the addition of a constant frequency to the original waveform. The second defect we consider is audio hiss. This is the addition of white noise to the original waveform. The third defect we consider is audio distortion. This is the clipping of the original waveform to a maximum and minimum value. The final defect we consider is audio clicking. This is a large abrupt transition in the amplitude of the original waveform. We consider 2 different versions of audio clicking. The first, additive, is the addition of an impulse to the original waveform. The second, reductive, is an abruptive transition caused by the removal of samples during the editing process. Now moving on to the model. We formulate this as a 5-class classification, where the predicted class is the class with the maximum likelihood given the data. The 5 classes are those highlighted previously: no defect, audio hum, audio hiss, audio distortion, and audio click. The likelihood function, fx, is a pre-trained audio neural network, PAN, and it's of the form CNN6. PANs are a framework of convolutional neural network architectures used for audio classification. We chose the CNN6 instance because it offers high throughput, which is vital for our use case. As illustrated on the left-hand side of the slide, the input to the CNN6 is the log-mel spectrogram of a 1-second audio clip. We utilize transfer learning to benefit from the pre-training on the large-scale audio set dataset. We replace the final layer with fully connected layer with 5 outputs, and then optimize the model by minimizing the negative log likelihood. Now we move on to discuss the dataset we use to develop and validate the model. It is important to note that the dataset is not comprised of real audio artifacts. Audio artifacts are rare in Prime Video content. Therefore, it would be challenging to collate a dataset of real audio artifacts large enough to train a deep neural network. Instead, we simulate each of the defects using algorithms proposed in the literature. These algorithms take a video and inject intervals that exhibit the defect. Each of the algorithms is mutually exclusive, so defects cannot occur concurrently. I do not have time to talk about each of the simulation algorithms now, so please see the paper for more details. The dataset itself is constructed of 1-second audio clips. We use 162 parent videos totaling 127 hours of clean, defect-free video. The parent videos are each assigned to one of the train, validation, or test sets. All artifacts created from a parent video belong to the same corresponding set. To construct the no defect class, we split each parent video into 1-second clips. To construct the defect classes, we apply each of the simulation algorithms to each of the parent videos and then split the resulting video into 1-second clips. We then compare each 1-second defective clip with the corresponding no defect clip. If the two clips have any differences, then the clip is added to the dataset. This step is necessary because the defect does not necessarily affect all samples in the interval. The table at the bottom of the slide indicates the number of samples in each class across the 3 datasets. The total trained dataset is constructed from approximately 1.25 million 1-second clips, the validation dataset approximately 410,000, and the test set approximately 780,000. We assess the quality of the model using the balanced accuracy. The average recall across all the classes. Over the test set, we observe a balanced accuracy of 0.986. Focusing now on the results for some of the individual classes in the confusion matrix on the left. We achieve a recall of greater than 0.99 for both audio hum and audio hiss. However, the recall for audio distortion is lower at 0.976. 1.7% of the time, the audio distortion are predicted as no defect. Distortion has a sparse effect on the waveform. It only affects a fraction of the samples in the clip. We hypothesize that the chunks that are incorrectly predicted as no defect may have a very small fraction of distorted samples. Now I will talk a bit about future work. Firstly, while our defect simulation algorithms were derived from literature, we have not validated that they are aligned with a viewer's perception of a defect. For a perception study, we will refine our simulation methods to more accurately reflect common audio defects observed in streaming video. Second piece of future work, we recognize the weakness of both developing and validating the model using simulated data. When transferred to real data, the domain shift may restrict the ability of the model. We chose to develop the model using simulated data due to the challenges associated with developing a large enough training dataset. However, we do not require as much data to simply validate the model. Therefore, we will create a dataset of real audio artifacts so we can validate the model's performance in real streaming video. Finally, to finish, I want to highlight the key takeaways of this work. Audio artifacts refers to sonic material that is accidental or unwanted. This may be introduced during the production process or subsequently in the editing process. Audio artifacts can have a negative impact on a viewer's quality of experience. Therefore, we want to identify and mitigate these problems. In this work, we present a no-reference model for detecting audio artifacts. Our model, based on a pre-trained audio neural network, identifies 4 different audio artifacts using only 1 second of audio. These audio artifacts are audio hum, audio hiss, audio distortion, and audio clicks. The developed model achieves a balanced accuracy of 98.6% over our proprietary test set. Thank you for watching.